This is the dynamics problem where you have an angled applied force causing an object to accelerate. As with any dynamics problem, we're looking at forces acting on an object. We want to consider whether the object is accelerating. And in this case, we have a sled being pushed at an angle, and they do in fact accelerate. So we're going to start with our free body diagram to organize what forces are on this sled. And again, when you have a free body diagram, we need to know, is it accelerating? In this case, there is an acceleration. Let's say it's accelerating to the right, which means you should have an unbalanced force to the right to cause that acceleration. So I'm going to draw the sled. The thing that is getting the applied force is our sled. We can put the little kid on here. All right, riding the sled, he's getting pushed by his brother. And remember, on a free body diagram, we only have the object that is accelerating, or the object that is being pushed or applied, and all the forces acting on that object. So I'm not drawing the brother pushing. I put the dotted line here to indicate that we're on a surface, but beyond that, you really shouldn't have anything else. So let's start putting some forces on here. The first force we are going to put on there is almost always going to be gravity, or weight. We call that Fg, or the force of weight. They tell you in this problem that the little brother weighs 220 newtons. So we actually know the length of this arrow is 220 newtons. We're on a surface. We're going to have a normal force. We're going to have friction. But to determine how much is going to be there, we need to know what this applied force is doing. So in this case, you're getting an applied force at a slightly downward angle of 30 degrees. So I'm going to draw that. It's 100 newtons. So I'm going to draw it about half as long as that gravitational force. I'm going to angle it slightly downward. And the angle that it makes, there's my 30-degree angle. And this is my applied force of 100 newtons. So when we get an applied force, remember we want to consider what's happening in the x and y direction in these dynamics problems. So really this applied force we can think of as a force that acts slightly down. That would be the applied force in the y direction, and slightly right. That would be the applied force in the x direction. Right, and so with that in mind, that allows us to determine what those other forces are going to be. So let's look at what's the normal force at this point. Now again, the normal force is what the surface is applying back to our object, and if it wasn't getting pushed, it would just balance gravity. But in this case, we have a downward push slightly. That applied force in the y is slightly down, which is going to make that sled feel heavier to the ground. The ground is going to have to compensate and actually push a little harder. So I know that that normal force is going to be upward and actually longer than the weight, or the force of gravity, because it's being pushed down a little bit. We also know that we have friction in play here. So friction acts along the surface. It resists motion. If this object is accelerating to the right, we have friction to the left. And we know that in this tug of war in the x direction, that applied force in the x should win against that little bit of friction. So I'm going to draw friction in here. I'm going to draw it fairly small. And so now we know that we have the applied force in the x is winning that tug of war. All right, so now let's look at how we're going to actually set up this problem. They want to know the coefficient of friction. All right, the coefficient of friction is called mu, and it is the ratio of the friction over the normal force. So in this problem, we need to find both of those forces. We'll divide them and get an answer. So how are we going to set this up? Well, Newton's second law says that the sum of all forces is equal to m times a. But because we are dealing with forces in two directions, we're going to split this problem up. We're going to look at all the forces that cause that mass to accelerate in the x direction, and look at all the forces that cause that mass to accelerate in the y direction. So now we have two parts of a problem, and we'll look at the variables in play at each one. You have the mass, you have the acceleration in the x, which in this problem we know the acceleration is positive 1.4 meters per second squared. That's the acceleration along the surface. And let's look at the forces along the surface. We have the applied force in the x, and you're going to have friction, the force of friction here. All right, so those are the x forces that are causing the acceleration. And in the y side, you have the same mass. You have an acceleration in the y, but it is not accelerating the y. This sled is going to stay on the surface, so we can put a 0 here. And then let's put the forces that are in play. You have that applied force in the y direction. You're going to have the normal force. Get my pen to work here. Change my color. You have a normal force, and you have the weight, or F G. Right? So really this is a table of variables that are in play in this problem, and we need to start filling some things in here. We do know that gravity acts downward, so I'm going to put a negative here. Now this is where we need our signs. Notice in my free body diagram the arrow accounts for the negative, but when I'm dealing with the math on the right, I'm going to make sure that the signs are correct. In this case, the applied force I expect to be negative, and the normal force I know is going to be positive based on how I drew it in my free body diagram. I know that friction is going to be negative, so I can put a negative here, and that applied force in the x is going to be positive. So again, getting the signs right is a good first step. What about that mass? Well, they told you the weight of this sled. We know that Fg is always equal to the object's mass times the acceleration due to gravity. In this case, we know the weight is downward at 220 newtons. We don't know the mass, but we know the acceleration is also downward at 9.8 if it was just in free fall, right? So if there was the only force, that mass would be accelerating downward. And so we can use that to calculate the mass by taking 220 and dividing by 9.8. And when you get that, you get a mass of 22.45 kilograms. M is equal to 22.45 kilograms, and I can put that right into here into my table. And I can put it in both spots, and we'll talk about how we're going to use those. All right, so I know the mass. What about that applied force? Well, here we need to do a little bit of trig. All right, so if I take that applied force, it is down at an angle. It is 100 newtons, and that applied force has a piece in the y, and it has a piece in the x. And if this is 30 degrees, then the applied is my opposite. The applied in the y is the opposite. So my applied force in the y is going to be the hypotenuse times the sine of 30 degrees. And the applied force in the x is going to be the hypotenuse times the cosine of 30 degrees. And I can write in those values in my calculator. Sine of 30 is 1/2, so I know that this is going to be 50 newtons. And I'll calculate 100 times the cosine of 30. And I get 86.6 newtons. Remember, always be in degree mode in your calculator. So now I can plug in that in the x direction I have 86.6 newtons, and in the y direction I have 50 newtons. Now notice the sign for that 50 is negative. The length of the arrow is 50. The sign is negative. It points downward. All right, so where do we go from here? Well, now in my table, I have on my y side, I have everything except the normal force. And remember, I want mu. So I need the normal force and I need friction. And I have everything except friction. So now I can use Newton's second law and I can actually solve for the missing pieces. So on the right side, Newton's second law says that the sum of all the forces in the y direction, well, that's the applied force in the y, plus the normal force, plus the force due to gravity. Those are the forces that are adding together. They're going to cause that mass to accelerate in the y direction. That's what that sigma f means. Add the vectors together. These are all y vectors, so I can add them up as numbers. And now we can plug in the values that we know. The applied force in the y is downward at 50 newtons. My normal force is what I don't know. I should get some big upward amount of normal force. Fg is downward at 220 newtons. And my mass of 22.45 is going to be multiplied by 0, so that side goes away, right? And so when I do a little bit of math, I get 270 newtons is what my normal force must be. It becomes positive 270 newtons. I can write that right in here. So I'm halfway there. And now what are we going to do with this other piece? Well, I'm going to slide down in here, and I know that the sum of these forces, Fa and the x, plus friction, is equal to the mass times the x acceleration. And I know the force applied in the x is 86.6 newtons, plus my unknown amount of friction, I expect that to be negative, is equal to 22.45 times my acceleration, which is 1.4 meters per second squared. And so I can multiply the right side, 1.4 times 22.45 and I get my net force to be 31.43 newtons. 86.6 plus friction has to equal 31.43. And so if I subtract 86.6 from that, I get 55.17 as friction. Friction becomes negative 55.17 newtons, which again, when I looked at what I expected it to be negative. And so we have 55.17. And so now I have the two pieces that I need. And I know that if I want mu is the ratio of friction over the normal force. And I know both of those now. Friction is 55.17 newtons. The normal force is 270 newtons. Now remember, I like to put these absolute value bars. I just want how much. So notice I don't need the negative signs anymore. How much friction? Friction is 55.17 newtons. And so when I take that ratio and divide that by 270, I get a ratio of 0.204. Mu is equal to 0.204. That is the coefficient of friction between the sled and the snowy surface. So there's all the work. I'll zoom out here. You can take a look at what we have here. About as complicated as we're going to go with these types of problems here. But you have an angled force. Again, most importantly, is look at that free body diagram. You expect that normal force to not be equal to Fg in this situation. That angled force you need to split into x and y pieces. And then we're just using F equals ma in each direction, treating them as separate problems. And mu, that coefficient of friction, is just a way to connect the friction and the normal force.